let's use Green's theorem to evaluate the integral over c of x squared minus y squared dx plus 2xy dy. So can you identify p and q from the vector field components when this is differential form? Can you identify p and q? Yeah, p is the x squared minus y squared, right? X squared minus y squared. And then q, so it's, now don't think it's always going to be the first one. There's no reason why you can't reorder it. So it's the guy, p is the guy attached to the dx, right? That's what we use for labeling. And then q is the guy attached to the dy. All right, so what does our little result tell us to do then? Yeah, remember how I used the lame analogy, you gotta be a formula whisperer? Well, okay, or let the formula whisper to you, whatever I said the other day. It's true though, right? Look at that double integral. We're gonna use that double integral to evaluate the line integral. And what does that double integral tell you to do? Look at it from the inside out. Find the partials for partial credit. Okay, so dq dx. What's the derivative of q with respect to x? So focus your eyes on q over here next to the dy. With respect to x, so it's 2y. Yeah. And then what's the derivative of, say, p with respect to y? Negative 2y. So the integrand, I'll go, I won't always label it like this, but I'll go ahead and do it here. The integrand to Green's theorem then would be dq dx minus dp dy, so 2y minus negative 2y, 4y. So we have our integrand. Now, I can try to start creating my double integral, but I need maybe to draw the region. I actually could figure it out without drawing the region here. But it's a good habit and a good way to get partial credit to draw the region that we're talking about. So let's see if we can draw the region that R encloses. Does anybody remember what R equal 1 plus cosine of theta, what that graphs to be? It's one of those. Is it a cardioid? It is a cardioid. You win. If I had a prize, I'd give it to you. So it is a cardioid. Now, if you forget what it looks like, the good news is you have a polar mode on your calculator, right? But I think we could probably figure out a general idea what it looks like. If you know that that's, by the way, back in my day, we had to memorize what these looked like, didn't we, Rob? So I'll bet with plotting a couple of points, if you know ahead of time it's a cardioid, a heart-shaped graph, I'll bet with plotting just a few points, you could figure out the basics of what it looks like. Let me do this. Let me put in an XY plane here. Even though it's a polar graph, you can graph it nicely on an XY plane too. And let me back off the view so we've got enough room here. And let me go ahead and make a table. R theta. And you know what? I'm going to be lazy here. I'm just going to plug in the corners. Do you know what I mean by that? I'm going to plug in theta at the corners. They're not really corners, but 0, pi over 2, pi, 3 pi over 2. Okay. So I'm going to be lazy here. 0, pi halves, pi, pi. 3 pi over 2, and 2 pi. Okay, so remember, we're plugging in theta because this thing's solved for r in terms of theta. R equals 1 plus cosine theta. So, okay, what's the cosine of theta? 1 plus 1, 2, so r is 2. Okay, plug in pi over 2, what do you get for r? Just 1, because cosine of pi over 2 is 0 plus 1. Plug in pi, what do you get? 0. Plug in, we actually have enough to graph it right now if you remember that it's going to be symmetric with the polar or x-axis. But let's say you don't remember that. So plug in 3 pi over 2, cosine 3 pi over 2 is 0, so you just get plus 1 again. 2 pi, you get the same thing you'd get if you plugged in 0, so 2. And then, all right, let me make my graph a little bigger here so you can see it. Okay, so remember, when you graph, you have to think radially and angularly when you're in polar coordinates. So look over in the direction of 0 radians over here, you're going to go out a distance of 2, aren't you? And then when you look straight up from the origin, that is, in the direction of pi over 2, you're going to go out 1. And then you're going to be at 0. You're going to be at the pole or at the origin when you plug in pi, right? Because r is 0. 3 pi over 2, you're going to be looking straight down and then going out a distance of 1. So it'll, or you could think of it as the reflection of that point. And then you're going to swing back around. So I'm not sure how wide it gets, but I know that it's kind of a sideways heart shape like that. And kind of went off. Have an eraser handy when you do these. A little too far down, but it's good enough. So what Green's theorem says is this line integral should be equal to a double integral, because that curve C satisfies the hypotheses. And by the way, P and Q do too. The derivatives will be continuous. That won't be an issue here. Okay? Now, let's set up the integral. So that the line integral with respect to the vector field, f dot dr, is going to be equal to, by Green's theorem, the double integral. I'm going to leave it over r of 4y. So this is a generic setup, right? dA. Why didn't I specify my limits of integration? Because I'm going to switch to polar, and I don't want to take the time to set it up with respect to rectangular coordinates. So I'm going to switch to polar now, which makes my area element what? RD theta. Okay, and then I'll pull the 4 out front, and then what is y? R sine theta, so you have to make that substitution. Okay, and now for your limits of integration, put in, I like to put in just a representative spoke. You could think of it as a sector if you want. And the endpoints of that spoke will give me my inner limits of integration. So what's the value of r closest to the origin? In that spoke, it's 0, right? And then on the edge, this value, this r value gives you? It's variable. 1 plus cosine theta is your upper inner limit. And then what would theta run from for the outer limits? 0 to 2 pi. Okay. So there's our setup. Okay, let's evaluate this thing. So, well, let me go ahead and rewrite it. So integral 0 to 2 pi. Oh, don't forget the 4 out in front. Integral 0 to 1 plus cosine theta. And then r squared, I'll put that right here, dr d theta, and I'll leave the factor of sine of theta in front of that, like that. Okay, let's integrate. 4 integral 0 to 2 pi, and then you said r cubed over 3, right? What should I do with that denominator of 3? Pull it out front. Let's not mess with that. And so we get sine of theta outside the evaluation brackets, and r cubed evaluated from
0,
yeah, and then dr is not there anymore. D theta, everybody with me? Is that okay? All right, so then inside the 0 is not going to do much for the lower limit. You're going to plug in the upper limit first. So copy everything down at 4/3 integral 0 to 2 pi sine theta, and then it'll become what? Times 1 plus cosine theta cubed. Now, I don't know about you, but I don't want to multiply that out. So, well, you can do it if you want, but let's go ahead and just use a u sub here without actually making the u sub, right? So what would your u sub be here?
1 plus cosine theta.
Yep. And so that's your u. What would your du equal? Negative sine theta, d theta. So we almost have a perfect du. We have a sine theta, d theta. Let's put the negative in there. and then like that. Now, this is a step I don't usually show, but it might, if you do it, you might start to get more comfortable. So I'm going to rearrange the multiplication inside here. Again, not necessary at all if you're comfortable with this. So -4/3, integral 0 to 2 pi. I'll write the u cubed. I'm not actually making the substitution, but 1 plus cosine theta cubed is my u cubed, right? And then I'll write the negative sine theta in parentheses so it doesn't look like subtraction right next to d theta. And then, so if a lot of you aren't quite comfortable not making the substitution yet, so this is the next best thing to making the substitution, realizing that's u cubed, and then that's your perfect du right there, right? So that reminds you what to do. Oh, it's just the 1 plus cosine theta. I'm going to use the power rule on that, right? Because 1 plus cosine theta cubed, it's u cubed. So what do you get without actually making the substitution for an antiderivative here? Yep, 1 plus cosine theta to the, okay, that to the 4th power, and then I should put that division by 4 outside, so I'll put it in as a factor in the denominator right there. Is that okay? And then, well, negative, right? And then 0 to 2 pi for my evaluation. Okay, so we get what out front? You said it, -1/3, I think, right? Yeah, gone. And then, okay, what happens inside when we plug in the upper limit? So we get cosine of 2 pi is 1, and then we have the +1 in front of that, so 2 to the 4th minus, what happens when we plug in 0? Oh, wasn't that nice? We get 0. Some students get disappointed. You do all this work and you get 0, but hey, it happens. If this represented some sort of work done, then we're saying 0 work is done by the vector field, right? Any questions on all that? We got it almost all on one screen.